class, this video is going to help with La Hopitals rule, which is, well, I put 4.3. It's 11.3 in the textbook I'm using right now, and or 4.3, depending on which textbook. Anyway, so for today, it is in the other 11.3 for the other textbook I'm using today. All right, so what is La Hopitals rule? Well, we've been doing all this stuff about graphing, and now we're kind of throwing in a little different idea in what this rule is, and it does have to do with graphing a little. What it is what if we're trying to take the limit of something that is in that indeterminate form from the very beginning of the semester? So it's 0 over 0 or infinity over infinity. What if it's in that form? Well, now that we know derivatives, we can actually find that limit. Where is that graph going with derivatives? So we have now a new way to find where our limit's going. So we have to have La Hopitals rule. Oops. Is for indeterminate forms. Okay, so La Hopitals rule is for, that's 0 over 0 or infinity over infinity or negative infinity over negative infinity, any infinity over infinity or 0 over 0. Okay, so these right here are all of our indeterminate forms. So let's look at what I mean by this. Well, I'm going to write this out in, so basically if we have the limit as some function as x goes to c, right? If whatever this function is, as you go to this value c, it's going to 0. And if we have the limit as x goes to that same value c of g of x is going to 0. So x and g are both going to 0 as you approach c. Okay. Then the limit as x approaches c of f over g is going to equal, oops, it's going to equal 0 over 0, right? So that's our indeterminate form. So the derivative of one, the derivative of the other, they're both, not derivatives, excuse me. The limit as both of those are going to c are 0. So then this would be 0 over 0. And what we can do is we can actually find this as the limit as it approaches this value of doing the derivative of the top over the derivative of the bottom. So basically, we can simplify the top and bottom by doing the derivative. Right, so let me show this in terms of an example. So if I'm at the limit as x approaches 4 of x squared minus 16 over x minus 4. So when we first look at something like this, we're like, oh, just plug in the 4. So if we do that, we'd have 4 squared, which is 16 minus 16, that's 0. And 4 minus 4 is 0. So this currently is in indeterminate form of 0 over 0. We can't do it. So the only thing we could do is factor, which this one you could factor, but I want to use the new method. You could factor and simplify, and if it wasn't factorable, we had a square root and some other things, we did multiplying by the conjugate, and that was like kind of a long process with algebra, and we don't love that method. So what we're going to do, or if we can't use either of those and it's even harder, then what we can do is take the derivative of the top and the derivative of the bottom and take the limit still. So it doesn't change our limit to do the derivative. So on the top, we'd have 2x and the 16 would drop off. On the bottom, we would have 1. Okay, so Then we could put that 4 in, which would just be 2 times 4 over 1, which is just 8. If we factored this, it would be x plus 4x minus 4 in the top. The minuses would cancel. You'd put the 4 in, you'd still get 8. So yes, we could still use that other method. Now, you can only use this method with limits. We're doing the derivative on the top, derivative on the bottom, but only with limits in indeterminate form. We still have the quotient rule, and you can't just throw this in other places. So it has to be indeterminate form in order for this to still get us the same solution as factoring or another method would get us. So what if I have, let's try the limit as x approaches infinity of 5x plus 4 over 6x plus 9. So here's our problem. Paper real quick here. Okay, so there's our problem. And right now, if I put in infinity on the top, infinity times this plus this, it's going to go to infinity. It's going to grow, 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 grow. Same down here. So this is going to be in the indeterminate form of infinity over infinity. Okay, so we had a shortcut where you could say, well, then it's basically going to 5, 6, which it is, but we want to use this new rule. If we did the derivative over the top, over the bottom, as x approaches infinity, we would go to 5 over 6. Oops, I wrote 5 over. So our answer is 5/6. Now, of course, a lot of people got these wrong on our first test because it really confused them that thought that it's going to 5/6 because these both had the same power. So now we have a different way. We can do the derivative and look, it goes to 5/6. Okay. Let's do one. All right, let's see. This one is, I was trying to think. What if I have the limit as x approaches infinity of x to the 12th over the natural log of x? X to the 12th over the natural log of x. So can you visualize that the top would keep growing as that x gets bigger to infinity, and the bottom would keep growing as well? So this is going to infinity over infinity. So I know I can use my rule. So what we can do from here is do the derivative of the top over the derivative of the bottom, but this still is the limit as x approaches infinity. So if we did the derivative on the top, you would get 12x to the 11th. If you did the derivative of natural log of x, it's 1 over x. Okay, well, 1 over x, if we flipped it and multiplied by the top, we would have the limit as x approaches infinity of 12x to the 12th over 1, right? Because 1 over x, you think of it as x over 1 times here. So there we go. And if I put in infinity, I can see this is going to infinity. Okay. I don't know that we ever did one like that because it was just hard. So what we usually did was one that could factor. So this is completely a new one. So it started out infinity over infinity, so we could use our rule, and we ended with infinity. It's going to positive infinity. Okay. One more example that I'm going to do, and then there's a bunch more video examples that you can watch if you need more help. The hard part is if you Google this idea, you're going to get a lot of sine, cosine, and the traditional calculus problems where this is business and we don't have the sine, cosine. So you might be able to get the general idea if you Google this topic, but it'll be a little harder to find problems. So I would stick with videos from me in the book. Okay, so limit as you approach 0 from the positive side of x times natural log of x to the 3,500. So right now, we can't use our rule, so we want to write it as a fraction to use the rule. And I know you wouldn't have thought of that. That's why I'm going over this one. So I want to write this as a fraction. So I'm going to move this one to the denominator. So follow me here. I'm going to leave natural log of x to the 3,500 over x to the -1. Still the same limit from the positive. So if I looked at this and I put a 0 in, we would end up with infinity over infinity. I'm trying to think of how to explain to you how we got infinity over infinity. Probably should have thought of that before I started my video. Okay, so if these numbers, if this is a 0 from the positive side, we would put in numbers like 0.1, 0.11, 0.111, and we could see that it's going to infinity over infinity. So it is in the indeterminate form. So what we can do from here is take the derivative of the top and bottom. So it's still a limit as x approaches 0 from the positive side. On the top, though, we're going to bring down the 3,500, and then it would be by the natural log of x, and that the derivative would be 1 over x. Okay? So you have to bring the exponent down, then do the 1 over x. A lot of people keep that exponent in the denominator, which is not correct. Okay, so basically it stays as your numerator, because this is like this over 1. On the bottom, you're going to have a negative x to the -2nd. All right, and right now, I am looking at this, and I'm going to simplify this. So this needs to go downstairs, and this can go back upstairs. I'm going to simplify this. So I'm going to think of this as 3,500 over x over negative x to the -2, okay? Which this is the same, I should have wrote it on this one, as 1 over x squared. So I'm going to flip that over, and I'd have 3,500 over x times negative x squared over 1. So we can simplify that. That x goes in here, and I get negative 3,500x. Okay, and then, woo, I can put in, finally, my 0, which means it's going to 0. And because it's from the positive side, we could put in our 0.1, our 0.11, and see what's happening as we get close to 0, or put in the 0, and we could see this is actually going to 0. I really wanted to show one of these where you have to write it as a fraction and then simplify after you do the derivative to really get to a place where you can solve putting in that final answer there. And we can see that we can actually use this rule from the positive, the negative, as we go to any number from any direction. If you have indeterminate form, you can do the derivative. Another thing, you could do the derivative more than once. So the rule is, like, if you're still in indeterminate form, you can do the derivative again and again on the top and the bottom until it's something that you can simplify easily. All right, so there's a lot more examples in the program, so I'm going to stop here, and hopefully this helps you with this section.